Hello and welcome to Lesson 35, Derivatives of Sine and Cosine Functions. So we've gone through all the rules. Now it's time to move into different types of functions. We've been dealing with polynomial and rational functions, and we still have a couple other types of functions we need to look at. So today I want you to be able to understand how the derivative of sine and cosine is developed. So that's more of you need to see where it came from, and more importantly, you can determine the derivative of a trig function. So that's the last part of the lesson today. So first what I'm going to do is I'm going to derive the derivative of sine just from its graph. So if we use an amplitude of 1 to negative 1, and we go, I'll spread it out a bit here, 90, 180, I'll use degrees to make everyone a little bit more comfortable here. Okay, so I want to just sketch the sine graph. So the sine graph starts at 0, 0, 1, 0, negative 1, and 0. And if you draw a nice smooth curve, you get a graph that looks like that. So what's the derivative equal to? What's y prime? Well, we talked about this earlier. The derivative we can find by finding slopes. So the easiest two slopes here are the zero slopes. So at 90 degrees, the slope is going to be 0. And if I set this up the same way, I should set up the scale here. So 90, 180, 270, 360. So at 90 and 270, slope is 0. So up here on the y-axis, on the original graph, we have our y and x values. All right. But now, instead of a y value, it's the value of slope, which would just be m. So our slope m and our x. All right. Okay, now what do we do to fill in the blanks here? Well, I'm going to do an approximation, and I mean, if we were to take time and make a really accurate graph, it would look a little bit better. But if you look at the tangent lines through 0 and 180, if you look at the scale, it turns out it is a one-to-one relationship, so the slope is actually 1 when it crosses the x-axis. And like I said, if I felt it was worth taking the time to develop, we can actually graph it out really, really carefully, and I'd have you draw tangents, but that's really not the case here. So what happens when I connect the smooth curve through the given points?
Can we just do color contact in the office, please?
We end up with a graph that looks like that, and hopefully some of you are saying, hey, I know that one. That is our cosine graph. Cos x. So graphically, that's what it would look like, and we know that if y equaled sine of x, y prime then would equal cos of x. So there's your first derivative property for trig functions. The derivative of the sine function is the cos function. So that's a graphical approach, and in the next example, I'm going to do it from first principles, just so you get to see how the just the different methods that are involved here. So now I'm going to go back to limits, and remember limits is your x plus h minus f of x, all divided by h. So the limit as h approaches 0 for cos of x plus h minus minus cos of h, all divided by h. Now here we're going to have to use our trig identities. Okay, so the trig identity we're looking at here is what is your cos of x plus h equal to. So we're going to use our addition formulas from the trigonometry unit in the functions from last semester. And that's going to write out or become cos x cos h minus sine x sine h minus cos of h. That's all divided by h. So we still have a problem, remember, with limits dividing by 0. So what I can do here, essentially what we're trying to do, remember with limits, one of the ways that we can get rid of problems is by writing sine h over h in terms of a limit, because that allows things to go to 1. So what I'm going to do is I'm going to break this apart into its components, or I'm going to group things together. So for example, I am going to group because of properties of fractions, and maybe I'll do all the steps here to start with. Cos x, cos h over h minus the limit as h approaches 0. Rather than skipping steps here, I'll show all steps since you're not here in front of me to ask questions. And the limit as h approaches 0 for cos h over h. So I just broke, and you can do this, right, because the denominators for all three of those numerators, so I've broken it into its particular fractions. Now, I noticed that this limit and this limit have a common factor of cos h. So I am going to group those together. I'm going to common factor it out. So the limit as h approaches 0 for cos h, and I'll have cos x minus 1 left in the numerator there. And that's all divided by h. Minus, and then the remaining fraction, I'm going to write it as sine h over h multiplied by sine x. So if we analyze that limit, and the reason we can is because I have sine h over h like I did before, that goes to 1, and as we evaluate sine of x when h is 0 just stays sine of x. There's no h in there, so there's no term to be concerned with. So my next problem and the next issue we've got to deal with is, what are we going to do with this? And that's our next focal point here. So in order to deal with this, we need to come up with some property that'll help us solve that. And we talked about if we have problems, we have tools in our tool bag to deal with this. So for this first one, this first term, the issue is that nothing cancels. So what do you do next? You try to factor. Well, there's no factoring here. There is no radical, but I can multiply by a conjugate to see if that conjugate will help us out. So what we are going to do here, I just want to double check to make sure I factored out the right term. And of course, I made a small mistake here. Up at the top, and some of you might have already caught it, minus f of x. So that should have been cos x, not cos h. So we're going to do a little bit of a quick fix here. And we don't really have to fix a whole lot up other than the fact that you still have cos x, cos h, and this will be cos x over cos h. And instead of factoring out a cos h, we're going to factor out a cos x. So that's the only thing we've got to switch here. So I do apologize for that. Cos x and then cos h minus 1. So cos x was the common factor. All right, so finishing this off then, I am going to multiply that expression by the conjugate of cos h minus 1. Because I can't factor, I'm out of options here. So I'm just going to show it in a different color. So I'm going to multiply the top by cos h plus 1 and the bottom by cos h plus 1. And then at the end here, this last term has become minus sine x, because there's no limit left to deal with in that last part. Okay, so just to clarify, this expression right here has simplified just to minus sine x. All right. Okay, so it's just this first fraction we're going to deal with here. So the limit as h approaches 0 of cos x multiplied by, it's a difference of squares, cos squared h minus 1, and that's all over h and cos h plus 1. So what happens with the cos squared h minus 1 on top? In red over here, it's just a trig identity. Remember that cos squared h minus 1, back from my 1 plus cos squared plus sine squared equals 1. This is going to equal negative sine squared h. So just your trig identity, which allows for, oops, I better not lose that minus sine x after all that work to get it, the limit as h approaches 0, cos x minus sine squared h over h cos h plus 1 minus the sine x So what happens now is we can now write sine h over h, and I'd be left with a cos x multiplied by negative sine h all over cos h plus 1. That term then goes to 1 for us. Oops, and I better not forget that negative sine x. Now in the denominator, if h goes to 0, so I'm looking in the denominator at this point in time. So if that goes to h goes to 0, that's just going to be a 1, so we're going to have 2 on the bottom, so we have no problems. What is sine of 0? Turns out to be 0, this term, which means that that whole first term goes to 0, and all that we're left with is the negative sine x. So therefore, if y is equal to cos x, the derivative of cos x is negative sine x. All that hard work just to find that out. So there are two different processes. Now the graphical one, we made some assumptions there because we didn't draw it accurately. This one is an exact process, but much more cumbersome, so we end up with the y prime. Y prime equals negative sine x. Now the one thing I want to add, and I believe I've got time, yeah, I'm going to add, if you can find a little bit of space here, the course says we don't have to know the derivative of tan. However, it comes up over and over, so I just tell people, you know what, let's just figure out what the derivative of tan is. So, that being said, y equals tan x. We don't know what the derivative of tan is, but we do know what sine x, tan is just sine over cos. So I'm just going to use the quotient rule here to figure out what the derivative is. So y prime, using the quotient rule, is derivative of the first term. So the derivative of sine is cos multiplied by the denominator minus first function multiplied by the derivative of the bottom function all over the bottom function squared. Cleaning up the numerator, cos squared x plus sine squared x over cos squared x. So we end up with 1 over, from trig identities, 1 over cos squared x. And we always write it as secant squared x. Then you don't have to worry about the fraction. So a quick summary off to the side here of this video. So the summary, if you have y equals sine x, derivative is cos x. If you have cos x, the derivative is negative sine x. And if you have tan x, the derivative is secant squared x. I'll write that a little bit neater. There we go. So there is the first segment of this video. Now we just need to go ahead and talk about the application. So that's how they're all derived. All right, and moving forward, we're going to then look at how to apply them in the next video.